Let's dive right in. Today we're tackling symmetrical short circuit analysis. Now, I know you already know the basics, but to really understand how we calculate complex fault currents today, we have to talk about the massive physical changes happening in our modern power grids. So, the fundamental problem we're facing is literally a shift in physics. For over a century, the grid relied on conventional synchronous generators. We're talking massive, heavy, spinning machines that gave us huge amounts of system inertia. But as we rapidly swap those out for renewables like solar and wind, which connect via power electronics, that physical inertia just disappears. And that drastically reduces fault current, making our traditional stability predictions incredibly tough. So here is our roadmap for today. First, the renewable grid challenge. Second, collapsing with Thevenin equivalents. Third, decoding asymmetrical fault currents. Fourth, finding the worst-case fault. Fifth, touch and step voltages. And finally, a quick look ahead at real-world unbalanced faults.
All right, part one, the renewable grid challenge.
The massive influx of renewables isn't just an energy shift, it's a dynamic shift. Because solar and wind use power converters, they offer very limited inertial support. Without that heavy spinning mass to basically push back against a grid fault, our frequency, voltage, and transient stability are all highly compromised. Moving right along to part two, collapsing with Thevenin equivalents. Okay, so how do you actually find fault current in a network with dozens of generators and hundreds of lines? Well, you absolutely don't solve it by hand. The core trick is using Thevenin's theorem to collapse the entire network into one equivalent voltage source and one impedance. And to do this efficiently, we build a bus impedance matrix, or Z-bus. You build one matrix once. And here's the payoff. The diagonal elements of that Z-bus directly give you the Thevenin impedance for a fault at every single bus in the network, with no manual resolving required. And this perfectly illustrates that collapse in action. We can take a terrifying real-world scenario, like a person touching a grounded structure during a massive fault, and reduce the entire rest of the grid down to a simple, solvable, closed-loop circuit. We're left with just the Thevenin voltage, the human body resistance, and the Thevenin impedance, which, in this specific case, is simply modeled as half the foot resistance. It's really that clean. Part 3. Decoding asymmetrical fault currents. Now, real-world faults are almost never perfect sine waves. When we break down an actual fault waveform, we see two distinct parts. There's the ideal symmetrical alternating current, and then there's a rapidly decaying unidirectional DC offset. Add those two together, and you get the massive, lopsided, asymmetrical fault current that totally dominates the first few dangerous cycles of a fault. Because that initial DC offset causes absolutely massive mechanical forces and heating, we use a decrement factor, or defect, to find the true RMS equivalent of that wave. But here is a huge warning. Mixing up your calculation standards here is a critical design error. IEEE and ANSI methods use a symmetrical current basis with empirical multiplying factors to handle that asymmetry, but the IEC 6909 standard? It uses a voltage factor method that accounts for maximum generator excitation. The exact same fault can give you completely different numbers depending on the code. If you run an IEC project with default ANSI settings, you end up with wrong equipment ratings, so always know your spec. Part 4. Finding the worst-case fault. To actually find that absolute worst-case condition for grounding design, the IEEE 82000 methodology gives us 4 really clean steps. Step 1. Determine your initial symmetrical current. Step 2. Compute the fault division factor to find out how much current actually enters the earth. Step 3. Find your decrement factor based on the fault duration. And Step 4. Multiply that decrement factor by the grid current. Boom! That establishes the absolute maximum stress your grounding system has to survive. Part 5. Touch and step voltages. Ultimately, all this complex math boils down to one thing: human safety. The IEEE standard defines maximum tolerable step and touch voltages, E-step 70 and E-touch 70, based on a standard 70 kilogram person. Our entire objective as engineers is to ensure that the actual voltage created by our maximum grid current never, ever exceeds these strict biological limits. But, it's crucial to remember that during a fault, not every single amp of that massive current shoots straight into the earth under our feet. That's where the current division factor, SF, comes in. It's the ratio of symmetrical grid current to total ground fault current. A large portion of that current is actually safely returning to the source via overhead ground wires and neutrals. Factoring this in is huge because it prevents us from wildly overdesigning our systems and wasting a ton of money. Finally, part 6. Next up,
real-world unbalanced faults.
So everything we've talked about assumes a perfectly balanced symmetrical three-phase fault. But those are actually the exception. That brings up a huge question. How do we handle the chaotic, unbalanced faults that dominate the real world? I mean, single line to ground faults account for over 70% of the actual faults you will ever encounter in the field.
Well, to decode those single line to ground faults, we use this exact formula. And right away, you can see we aren't just dealing with a simple impedance anymore. We have to account for positive, negative, and zero sequence equivalent system components. Introducing this zero sequence complexity completely blows up those elegant, simple Thevenin equivalents we just mastered. So, how do we solve a grid that is fundamentally out of balance? Well, that is exactly the puzzle we are going to unravel next time.